Hey there, we're on day 4 of our gas laws notes. Today we're going to do some gas stoichiometry problems, which you already know how to do, but we'll go back through them again. Let's see. Equal volumes of gases at the same temperature and pressure contain equal numbers of molecules. That is called Avogadro's principle. Molar volume is equal to 22.4 liters per mole. That means in 1 mole of any gas at standard temperature and pressure, the volume is exactly 22.4 liters. Now that's any gas. This means at 0 degrees C and 1 atmosphere, 22.4 liters will contain 1 mole of any gas. Or 1 mole of any gas will have a volume of 22.4 liters. We use stoichiometry with moles, grams, and molar mass. We use stoichiometry all over the place, and you guys are great at it. We're also going to use stoichiometry for reactions involving volumes of gas, which again, we've already done these, so it shouldn't be anything too terribly new. Important pieces, the coefficients in the balanced chemical equation represent the number of moles, and ratios of liters of gases, also assuming pressure and temperature remain constant. Direct mass to volume problems in which we use 22.4 liters equals or to 1 mole only work if the gas is at standard temperature and pressure, but no worries, we're not going to give you any gas that is not at standard temperature and pressure, so you're good to go. So according to the above reaction, this is number 1 down here, according to the above reaction, what volume of nitrogen dioxide gas is produced from the combustion of 100 grams of ammonia gas, assuming that the reaction takes place at standard temperature and pressure, which I told you that they all would. So we're going to box the given and circle the unknown. The unknown, volume of NO2, and box my given. My given is 100 grams of ammonia. Here's my balanced equation. So I start by writing my given, 100 grams of ammonia. And draw some chart there, my T-chart there. I just go down the unit so I know what goes next. So I put grams of ammonia in the denominator. Remember, that unit's got to go down there. And then I happen to remember that 1 mole is equal to the molar mass in grams. So what I need to do is find the molar mass of ammonia. So ammonia has 1 nitrogen. Let me get our calculator going here so you can see it. 1 nitrogen, 14.007, plus 3 hydrogens, 3 times the molar mass of hydrogen. I'll close my parentheses there. There I've got the molar mass of ammonia, 17.031. Once I have this into moles, I can use the mole ratio to go from moles of ammonia to moles of nitrogen dioxide. I just go down the unit, so I put moles of ammonia in the denominator. And what I'm looking for is volume of nitrogen dioxide, but I need to get that into moles in order to use the volume conversion. Okay, here are going to go my coefficients. So I go back to my balanced equation. There are 4 moles of ammonia and 4 moles of NO2. Okay, need a last little space there. So I just go down moles of NO2. I didn't leave enough space. In 1 mole of NO2, this is where we're going to use the conversion factor, 22.4 liters of gas. Okay, so what do? Just go down each time. Take whatever unit is in the numerator here, put that unit in the denominator. That guides your stoichiometry so you know what to use. Okay, now all these units will cancel. The only unit that hasn't canceled, see what, grams of ammonia, moles of ammonia, 3 moles of nitrogen monoxide, liters of nitrogen dioxide, sorry. That's what we wanted. So let's do some math here. We'll multiply everything in the numerator, 100 times 1 times 4 times 22.4. Okay, that's what's in my numerator. My denominator, let's see, I'm going to divide that by 17.031 times 4 times 1. Close the parentheses. Okay, let me do that. And my final answer, 131.524. 3 sig figs, so 132 liters of nitrogen dioxide. See? Just theirs is neater, so you can see that if you need to write that down. Okay, problem number 2. It's kind of an interesting one. Bombardier beetles use decomposition of hydrogen peroxide to defend itself. If 1.1 grams of H2O2 decomposes, what volume of O2 will be produced? Well, I'm going from grams of hydrogen peroxide to liters of oxygen. So I'm going to box my given and circle my unknown. Write my given. You see that? Yeah, everything's on there. 1.1 grams of H2O2. And I disco down my unit. Grams of H2O2 is in the numerator. Put it down here. Grams H2O2 in the denominator. I'm going to use the conversion factor 1 mole equals molar mass in grams. Okay, that's what I'm going to put right there. So I need to find the molar mass of hydrogen peroxide. So 2 times 1.008, 2 hydrogens. I'm going to add that to, open up the parentheses, 2 times oxygen. And I get 34.014 grams. 34.014 grams in 1 mole of N2O2. H2O2. Where did I get that? H2O2. There we go. 1 mole is the molar mass. Okay, now cancel my grams. Disco down moles of H2O2. Okay, since I've got moles down here, I can put moles up here. I'm going to do my mole conversion here. I need moles of oxygen though. So I use the mole ratio. I'm going to use the coefficients right here. There are 2 moles of H2O2 and 1 mole of oxygen. Okay, cancel out those moles of H2O2. I'm almost there, so I need to disco down moles of O2. I'm going to use this conversion factor now. 1 mole is equal to 22.4 liters. That's the conversion factor I'm going to use right here. 1 mole is 22.4 liters of oxygen. Okay, moles of O2 cancel. I'm left with liters of oxygen. So I start my math. 1.1 times 1 times 1 times 22.4. And I'm going to divide that by whatever's in my denominator down here. Open up my parentheses. 35.014 times 2. And it looks like 0.362. Let's see, how many sig figs can I have? I can only have 2. So my final answer is going to be 0.36 liters of oxygen. Now they're going to pop in your slideshow here. 1.1 grams. See, you disco down. There's the conversion to moles. Next will be my mole ratio. And finally, 1 mole is 22.4 liters of oxygen. And we get 0.36 liters of oxygen. Alrighty, example problem number 3. When 5 liters of oxygen is consumed, how many liters of carbon dioxide are produced? Well, 5 liters of oxygen is my given. My unknown, liters of carbon dioxide. Both gases are at STP. So we start by writing 5 liters of O2. Draw my chart. And disco down liters of O2. Okay, in this case, we're still going to use the 1 mole equals 22.4 liters, but we're going to flip it. Okay, we're going to put 22.4 liters here, 1 mole here, because what I need to do is I need to convert from moles of oxygen to moles of CO2. Now I'm going to use my mole ratio. Okay, I'm going to disco down moles of O2, and I'm going to put moles of CO2 in the numerator. So let's see, there are 3 moles of CO2 and 5 moles of oxygen. Okay, I got to go one more step. Need a little bit more space there. Moles of oxygen's canceled. Now I've got moles of CO2 and I disco down moles of CO2. I'm going to use the same conversion factor that I used back here. 1 mole of CO2 is 22.4 liters of CO2. Okay, so let's do the math. 5 times 1 times 3 times 22.4. And I'm going to divide that by, open up the parentheses, 22.4 times 5. 3. Okay, how many? Oh, look, I can have one sig fig. How convenient. There we go. And let's pop this in so you can see, nice and neat, what we did. Okay, last problem. If a scientist collects 48.6 grams of water, how many liters of oxygen were used in the reaction? So 48.6 grams of water is my given. Liters of oxygen is my unknown. I start by writing my given, 48.6 liters of H2O. Ooh, can't see that here. Let me put that on. There we go. Draw my chart. Disco down liters of H2O. That's the first thing I do. I need to convert this into moles because then I can use the mole ratio to get to oxygen. So I know that 1 mole of any gas is 22.4 liters. Now that I've got this out of liters and into moles, I'm going to use my mole ratio next. I disco down moles of water, and I put moles of oxygen in my numerator. I'm going to use my coefficients right here and right here to do the mole ratio of oxygen to water. So oxygen, 7, water, 6. Get rid of those moles of water. Last step, I need to go to liters. Oh, you didn't stop me. Why didn't you stop me? I would have gotten mad at you for my students. We're going from grams. What did I do wrong? I did liters. What a nut. So let's go back. We can do that. No problem. Eraser is a good thing. So 48.6 grams of water. Okay, everything's going to be the same. The only difference is instead of 22.4 liters down here, what do you think I'm going to put? I'm going to put the molar mass of water, okay, because I need grams. Yeah, stop me when I do dumb things like that. All right, so now my grams are canceled, okay, and everything stays the same. Now I'm going to do 1 mole of oxygen, finish up what I was doing here, 22.4 liters. Okay, hope I didn't scare you too much there. That was my mistake. I saw liters. I should have seen grams. All right, 48.6 times 1 times 7 times 22.4 gives me that number. Oh, how about that number right there? 7,620.48. And I'm going to divide that by what's in the denominator. What's in the denominator is 18.015 times 6. Yeah, there we go. So 70.5. 3 sig figs? Yep, 70.5 liters of oxygen. So if you need help with this, go see a teacher, but this should be old news to you. You guys have already learned gas stoichiometry, so this should be a gimme. Good luck. See you soon.